Ancient astronomers could predict eclipses with astonishing accuracy long before modern science existed. This video reveals the incredible story of how they achieved such uncanny precision, a tale of human intellect that reshaped our cosmic understanding. You will discover the sophisticated methods and forgotten tools that let them forecast celestial events centuries in advance. How did cultures separated by oceans and millennia crack the same celestial code? And what secret cycles did they uncover in the night sky? What does this ancient mastery tell us about our own quest to understand the universe? The night sky was their unchanging map, a grand clockwork of lights they studied with unwavering dedication. Without a single lens or modern instrument, these ancient sky watchers embarked on a project spanning generations. They tracked the sun's path, the moon's phases, and the wanderings of planets against the fixed backdrop of stars. In Babylon, scribes pressed careful notations into soft clay tablets, creating a permanent record of celestial events. In China, astronomers documented their observations on delicate silk scrolls, their ink strokes capturing the precise timing of a lunar eclipse or the sudden disappearance of the sun. What they were looking for, above all else, were patterns. They noticed that the heavens were not random. The same configurations of stars returned with the seasons. The moon waxed and waned in a reliable rhythm, and sometimes the sun and moon would meet in a dramatic, terrifying embrace, an eclipse. For these cultures, an eclipse was far more than a celestial spectacle. It was a potent omen, a message from the gods that could foretell the fate of an empire, the success of a harvest, or the health of a ruler. This deep-seated belief, blending fear and reverence, provided a powerful motivation to understand these events. It drove them to perfect their records, to compare one eclipse with the next, searching for the hidden order within the apparent chaos. Their patient, meticulous work did not simply catalogue the sky. It began to reveal its secrets, laying down the first stones on the path to a profound prediction. Their patient observations eventually revealed a celestial rhythm, a slow and steady pulse in the heavens. They discovered a cycle of approximately 18 years, 11 days, and 8 hours. This repeating clock is known as the Saros Cycle. Imagine the sun, the moon, and our Earth slowly dancing through space. After this precise Saros interval, the three bodies return to almost the exact same alignment. The geometry of their positions repeats, so if an eclipse occurred on a certain date, a very similar eclipse would be visible from Earth 18 years, 11 days, and 8 hours later. The Babylonians, with their meticulous clay tablet records, were likely the first to identify this grand pattern. They used it to create long-term eclipse calendars, forecasting celestial events decades, even centuries, into the future. Think of the immense dedication this required. An astronomer would begin his work tracking a particular eclipse. He would record its every detail, knowing he would never live to see its return. He was planting a tree whose shade he would never sit under. His son and then his grandson would continue the work, adding their own observations to the growing archive. It was a project that spanned human lifetimes, a testament to faith in a predictable universe. This cycle, the Saros, was their master key. It transformed eclipses from terrifying, random omens into predictable events. They were no longer mere messages from angry gods, but part of a natural, comprehensible order. This understanding was a colossal leap for humanity, a pivotal step in demystifying the cosmos. Yet, even with this powerful key in hand, the ancient astronomers faced another challenge. How could they apply this 18-year cycle to their own specific city or kingdom? Knowing an eclipse would happen was one thing, but knowing if you would actually see it from your home was another problem entirely. Deep in the heart of the ancient world, Babylonian astronomers pressed their wisdom into wet clay. These weren't simple notes, they were permanent celestial diaries baked hard by the sun to survive for thousands of years. On these tablets, they recorded the exact dates of eclipses, the precise hour they began, and how many minutes the moon spent hiding the sun or passing through the Earth's shadow. Each tiny indentation was a piece of a grand puzzle. They weren't just watching the sky, they were processing the data, searching for the mathematical heartbeats behind the movements. Their primary tool was the Saros Cycle, that repeating pattern of 223 lunar months. By tracking this long rhythm, they could look back at an eclipse from 18 years prior and confidently predict a similar one would follow. But their genius went even further. They noticed that not every eclipse in a Saros family was identical. The moon's path shifts slightly with each cycle. So they developed correction factors, little mathematical adjustments to their predictions to account for these subtle changes over centuries. This work was a sacred duty, deeply intertwined with the fate of their kingdom. An eclipse was a direct message concerning the health of the king and the stability of the empire. A predicted eclipse that failed to arrive was a good omen, a sign the gods were appeased. But an unpredicted eclipse was a terrifying event, a celestial shock that could plunge the court into panic, so their calculations served a dual purpose. They were both a scientific triumph and a vital tool of state security, a way to read the intentions of the gods and prepare for their will. These clay tablets are our direct link to their meticulous minds. They show us the first true scientists, patiently building a scaffold of knowledge that would support all of astronomy to come. From their fertile crescent, a new understanding of cosmic order began to spread, but it would find a very different expression on the other side of the world. Far to the west, the Greek astronomers approached the same cosmic puzzle with a different kind of genius. While the Babylonians perfected celestial arithmetic, thinkers like Hipparchus and Ptolemy sought to build a physical model of the heavens, a geometrical architecture that could explain not just when eclipses happened, but why. Their cosmos was not just a collection of data points, but a grand, spinning mechanism governed by mathematical law. To account for the moon's subtle speed changes and its slightly shifting path, they devised an ingenious concept, the epicycle. Picture the moon not simply circling the Earth, but traveling in a smaller loop, a circle upon a circle. This elegant idea explained why the moon sometimes drifted closer and sometimes farther, creating the small variations in its motion that were so critical for predicting the exact moment its shadow would touch the Earth. They also introduced the idea of an eccentric, a model where the Earth was slightly off-center from the moon's true orbital path. This was a profound leap. It moved beyond simple pattern recognition and into the realm of physical theory, attempting to describe the actual structure of space itself. Ptolemy's great work, the Almagest, compiled these geometrical tools into a comprehensive system. It provided detailed methods for calculating the moon's position and the sun's path with unprecedented precision. An astronomer using the Almagest could, in theory, compute the timing and visibility of an eclipse from any location, moving beyond the broad strokes of the Saros Cycle to a more localized, specific prediction. This was the true legacy of Greek astronomy, a shift from observing what the heavens did to theorizing how they worked. It was a marriage of geometry and observation that created a predictive engine, one whose core principles would guide our understanding of the cosmos for the next 1,400 years. Yet, even this magnificent model was not the final word. A new civilization was rising, one that would take these Greek insights and refine them to an even sharper edge, pushing the limits of prediction further than ever before. While Greek philosophers built models of the cosmos in their minds, another group of thinkers was building a model of it in bronze. Recovered from the depths of an ancient shipwreck, the Antikythera Mechanism is a corroded, fragmented puzzle that has rewritten our understanding of ancient technology. This wasn't a simple star chart or a ceremonial object. It was a precise, hand-cranked analog computer, an intricate clockwork of at least 30 interlocking bronze gears housed in a wooden case no larger than a shoebox. By turning a handle on its side, an ancient user could advance time forward or backward, watching as tiny spheres representing the sun and moon moved through the zodiac, the moon waxing and waning in its correct phase. And on its back, a sophisticated dial was dedicated to one of the most important predictions of all, forecasting the timing of future lunar and solar eclipses. This was the theoretical work of Hipparchus, and the data-driven cycles of the Babylonians made physical. The mechanism didn't just calculate dates, it modeled the very mechanics of the heavens, accounting for the moon's wobbling orbit with a brilliant gear design that mimicked its subtle speed changes. A small, labeled ball would even display the expected color of a lunar eclipse, a detail hinting at the atmospheric conditions predicted for that night. This artifact, likely crafted in the 2nd century before the Common Era, represents a technological peak that would not be surpassed for over 1,000 years. It bridges the vast gap between abstract astronomical theory and tangible, applied engineering. Here was a device that a ship's navigator or a temple priest could hold in their hands, a portable universe that translated complex celestial cycles into a simple turn of a crank. The Antikythera Mechanism is a powerful testament to a lost age of innovation, proving that the desire to predict the cosmos was so strong, it drove the creation of the world's first computers long before the modern era. But this incredible device was a secret lost to the deep for 2 millennia, a single, brilliant flash in the Mediterranean night. What happened to this knowledge, and how did the enduring human quest to understand eclipses continue in other corners of the globe? Across the world in ancient China, the stakes for predicting an eclipse could not have been higher. Here, an eclipse was not merely an omen, it was a direct celestial critique of the emperor himself. The heavens were believed to mirror the quality of imperial rule, and a darkened sun was a stark warning of heavenly displeasure. If the emperor lost the mandate of heaven, his dynasty could fall. This immense pressure transformed the royal astronomers into the most vital civil servants in the empire. Their task was not just to understand the cosmos, but to protect the state from it. They maintained meticulous records, with one-hand dynasty document noting an eclipse so precisely it was recorded as having begun at the hour of the dragon, just before dawn. These weren't simple observations, they were evidence presented in the celestial court of law. The emperor and his court relied on these predictions to perform elaborate rituals of atonement, beating drums and offering sacrifices to appease the sky and symbolically restore the sun's light, and with it, the emperor's legitimacy. This dire need for accuracy, driven by sheer political survival, fueled a technological race to build better instruments. A brilliant scientist named Zhang Heng answered this call in the 2nd century. He perfected the Armillary sphere, a complex bronze model of the heavens with interlocking rings that mapped the paths of the sun, moon, and stars. By aligning this instrument with the pole star, an astronomer could track celestial movements with remarkable precision, calculating the moon's path to determine exactly when it might intrude upon the sun. But Chinese astronomers went beyond just tracking cycles. They sought to understand the underlying principles. They developed a cosmology where the universe operated through balanced, interacting forces. An eclipse, in this view, was a temporary imbalance, a predictable event within a natural order. This philosophical framework allowed them to see eclipses as part of a comprehensible system, not just random divine anger. Their science and their spirituality were intertwined, each pushing the other to new heights. The imperial court's fear of the sky, therefore, did not stifle discovery. It bankrolled it, leading to one of the most sustained and sophisticated programs of astronomical observation the ancient world would ever see. And as this knowledge spread, it would eventually travel the Silk Road, reaching the hands of scholars in a new empire whose own hunger for celestial order was just beginning to awaken. Meanwhile, on the other side of the world, a civilization was charting the heavens with a mathematical precision that still inspires awe. In the dense jungles of Mesoamerica, the Maya developed a calendar system of such complexity it rivaled any in the ancient world. Their greatest astronomical secrets are preserved in a handful of surviving texts, the most famous being the Dresden Codex. This pre-Columbian manuscript, a long strip of bark paper folded like an accordion, contains a stunningly accurate eclipse prediction table. It is not based on the Saros Cycle, but on another repeating pattern, a cycle of 405 lunar months. This was their key to unlocking the future. The table lists potential eclipses, both lunar and solar, stretching far into a future its creators would never see. Each entry was a warning and an opportunity, a date when the cosmic balance was at its most fragile. For the Maya, an eclipse was a dramatic celestial battle. They saw it as a monstrous serpent or a jaguar devouring the sun or moon, a temporary triumph of chaos over order. The role of the priest astronomers was not just to predict this event, but to manage it. Armed with the knowledge from the Codex, they could schedule elaborate ceremonies to intervene. They would ascend their pyramid temples, dressed in sacred regalia, and perform rituals of bloodletting and offering to strengthen the sun god in his fight against the darkness. Their precise predictions were a form of cosmic diplomacy, a way to plead with the gods and ensure the sun's victorious return. This was science in service of survival, mathematics woven into the very fabric of their spirituality. The ability to forecast an eclipse gave them a profound sense of control over a terrifying universe. It transformed a moment of potential doom into a scheduled ritual, a managed crisis where humanity had an active role to play. How did they achieve this without telescopes or advanced metalworking? Their tools were observation, generations of meticulous record-keeping, and a gifted facility with numbers, including the conceptual leap of inventing the zero. The Dresden Codex stands as a testament to a unique intellectual tradition, a parallel path to the same destination reached by the Babylonians and the Greeks. It proves that the human mind, when driven by a deep need to understand, can find the same profound truths in the stars, no matter where on Earth it looks up. A similar fusion of cosmic storytelling and mathematical rigor was unfolding in ancient India, where the sky was both a spiritual canvas and a geometrical puzzle. Here, astronomers and mathematicians composed the Siddhantas, foundational texts that translated the grand movements of the heavens into precise, calculable algorithms. These weren't just philosophical musings, they were practical manuals for prediction, filled with step-by-step instructions for determining the positions of the sun and moon. At the heart of this intellectual revolution were brilliant minds like Aryabhatta. In the 5th century, he proposed a revolutionary model, suggesting the Earth was a spinning sphere and that the apparent rotation of the stars was an illusion caused by this daily spin. He calculated the value of pi to 4 decimal places and used trigonometry to map the celestial sphere, developing equations that could pinpoint the moon's location with stunning accuracy. A century later, Brahmagupta refined these methods further, providing clear rules for calculating the duration of an eclipse and even accounting for the parallax effect, the slight difference in the moon's position as seen from different locations on Earth. Their mathematics was sophisticated, employing algebraic formulas and trigonometric functions to solve problems that would challenge modern calculators. Yet this scientific fervor existed alongside a powerful mythological explanation for eclipses. In Hindu tradition, the celestial demons Rahu and Ketu were said to chase the sun and moon across the sky, occasionally catching and swallowing them, causing the light to vanish. This story, rich with symbolic meaning, did not stifle scientific progress. Instead, the two narratives coexisted. A priest could recite the epic tale of Rahu while simultaneously using Brahmagupta's algorithms to compute the exact minute the eclipse would begin. The spiritual narrative gave the event its cultural meaning, while the mathematical prediction gave the community a sense of control and order. This seamless blend was the hallmark of Indian astronomy, a tradition that saw no contradiction between exploring the universe through equations and understanding it through myth. The precision they achieved was not just for scholarly pride, it was essential for social and religious life, determining the exact timings for festivals, rituals, and agricultural cycles. Their work demonstrates that the pursuit of celestial prediction is a universal human endeavor, one that can flourish within any cultural framework, driven by the same fundamental desire to find order in the cosmos. As the classical world faded, a new beacon of learning ignited in the East. Islamic scholars did not merely preserve the astronomical knowledge of the Greeks and Indians, they set it into motion, refining it with a relentless focus on empirical accuracy. In grand observatories from Baghdad to Central Asia, astronomers like al-Battani dedicated their lives to correcting the ancient models. He spent over 4 decades making meticulous observations of the sky, discovering small errors in Ptolemy's calculations of the solar year and the moon's path. His work provided crucial corrections, sharpening the precision of eclipse tables to a degree previously unimaginable. This was not passive preservation, it was active, critical improvement. They translated the Almagest and the Siddhantas not to enshrine them as perfect, but to use them as a starting point for new discoveries. Al-Biruni, a towering intellectual figure, combined Greek geometry with Indian computational methods, developing complex trigonometric equations that could predict whether an eclipse would be partial or total from a specific location. He even discussed the possibility of the Earth rotating on its axis, a revolutionary idea for his time. Their greatest tools in this quest were new instruments of breathtaking ingenuity. The Astrolabe, a handheld marvel of engraved brass and finely crafted pointers, was their portable universe. A scholar could hold it up to the sky, measure the altitude of the sun or a star, and then use its rotating disks to calculate the time, the date, and even simulate the upcoming positions of celestial bodies. It was an analog computer for solving the practical problems of astronomy, timekeeping, and navigation. Through their work, the predictive power of Greek geometry was fused with the numerical agility of Indian mathematics, creating a unified and far more powerful science. This golden age of Islamic scholarship became the indispensable bridge, carrying the torch of cosmic understanding through the centuries and ensuring it would one day be passed to a waiting Europe. Yet even as the Islamic world perfected its instruments, the flame of celestial knowledge was kept flickering in the quiet scriptoria of medieval Europe. Here, isolated within stone walls, monastic scribes became the unsung archivists of the sky. Their world was one of prayer and parchment, where every unusual event was a potential message from God. When the sun vanished at midday or the full moon turned to blood, they carefully dipped their quills into ink and noted the event in their chronicles. The Venerable Bede, an English monk of the 8th century, studied these events with a scholar's eye. He understood that eclipses followed natural cycles, and he used this knowledge not for statecraft, but for the church calendar, calculating the movable date of Easter with greater accuracy. His work demonstrated that these celestial phenomena were part of a divine but predictable order. These monastic records, often penned in the margins of religious texts, accumulated over centuries. They were not driven by a quest for scientific glory, but by a duty to document God's creation. This theological motivation, however, produced an unexpected treasure, a continuous timeline of celestial events stretching back generations. When classical texts like Ptolemy's Almagest began to trickle back into Europe through Arabic translations, these old monastic chronicles were waiting. They provided the crucial data, the long-term observations from European skies that allowed scholars to test and verify the revived Greek models. The quiet diligence of a monk in a cold scriptorium, noting the hour a shadow fell across the moon, would centuries later help confirm a mathematical theory conceived under a Mediterranean sun. This long, patient chain of observation, stretching from Babylon to Baghdad to a Northumbrian monastery, was about to be handed to a new age, one poised to shatter the very cosmic model it had so carefully preserved. Then came a quiet revolution, not in an observatory but on the printed page. In 1543, a dying Nicolaus Copernicus was presented with the first printed copy of his life's work. His book proposed a universe that was fundamentally, shockingly rearranged. He removed the Earth from its privileged place at the center of everything and set it spinning around a central sun. This was not merely a new map of the cosmos, it was a philosophical earthquake. For eclipse prediction, the immediate practical gains were small. Copernicus still used circular orbits, and his predictions were not dramatically more accurate than Ptolemy's. But the real power of his model was its elegant simplicity. The retrograde motion of planets, the varying speeds of the moon, all these complex motions that required elaborate epicycles and equants in the old geocentric system, suddenly became natural consequences of an Earth in motion. The cosmic machinery, once a tangled web of circles upon circles, was now streamlined. This new framework provided a cleaner, more logical foundation for calculating the paths of the Moon and Earth. The mathematics of an eclipse, the precise alignment needed for a shadow to fall, became conceptually clearer when you started from a sun-centered system. Copernicus had provided the correct stage, even if he hadn't perfected the actor's choreography. His work forced every astronomer in Europe to confront a radical question. What if the ancient authorities, from Ptolemy to Aristotle, had been wrong about the most basic structure of reality? This intellectual rupture was essential. It cleared the ground, making room for a new generation of thinkers who would take this sun-centered model and use it to uncover the true laws of motion. The Copernican Revolution was less about immediate accuracy and more about unlocking a deeper, more profound truth, one that would ultimately give us the power to predict not just eclipses, but the dance of every planet and moon. Tycho Brahe built his own universe on a small Danish island. For over 20 years, inside the walls of his Uraniborg observatory, he compiled an atlas of the sky with an accuracy that was simply unprecedented. Using massive, custom-built brass instruments, he measured the positions of planets and stars with the naked eye, achieving a precision often finer than a single minute of arc. To put that in perspective, that is like measuring the width of your thumb held at arm's length against the entire dome of the sky. He tracked the moon's path with obsessive detail, recording its daily motion against the stars and noting every solar and lunar eclipse with painstaking care. His data was not just a list of events, it was a deep, quantitative map of celestial movements. Brahe was a man caught between cosmic models, rejecting the perfect circles of Ptolemy, but unwilling to fully accept the sun-centered system of Copernicus. So he crafted his own hybrid, a universe where the planets circled the sun, but the sun itself, carrying all those planets, orbited a stationary Earth. This strange compromise was not born from stubbornness, but from a profound respect for what his measurements actually showed. He could detect no stellar parallax, no shifting of the stars that a moving Earth should cause, so he concluded the Earth must stand still. His model was a testament to his guiding principle, to build a system of the world not from philosophical preference, but directly from the hard numbers etched into his observing logs. This unwavering commitment to empirical evidence created a treasure trove of data, a legacy of precision that would outlive him. When the brilliant but impoverished mathematician Johannes Kepler inherited this priceless archive, he gained access to a record of the heavens so exact it could finally test the old assumptions to destruction. What secrets would these numbers reveal when placed in the hands of a mind capable of seeing the patterns Tycho himself had missed? Johannes Kepler inherited a universe of numbers. Tycho Brahe's decades of meticulous observations were now in the hands of a theorist who saw not just data, but deep, hidden patterns. Kepler was a man driven by a belief in a mathematical god, a divine geometer who had built the cosmos according to elegant laws. He spent years wrestling with Tycho's treasure, particularly the stubborn motion of Mars. The planet refused to fit the ancient perfect circles. After a long and tortured struggle with the numbers, Kepler made a leap that shattered 2,000 years of astronomical tradition. The orbits of the planets were not circles, they were ellipses. This was his revolutionary first law of planetary motion. Imagine a circle gently pressed on two opposite sides, creating a slightly flattened ring. The sun does not sit at the center of this ellipse, but at one of its two focal points. This single insight explained so much. It clarified why the moon, in its own elliptical path around Earth, is sometimes closer and sometimes farther away. This varying distance is the crucial difference between a total solar eclipse and an annular one, where a ring of sunlight remains visible around the moon's silhouette. Kepler had found the true shape of the cosmic dance. His second law added the rhythm to this dance. He discovered that a planet does not move at a constant speed. It speeds up when it is closer to the sun and slows down when it is farther away. This principle of equal areas in equal times applied perfectly to the moon's motion as well, explaining the subtle variations in its speed that had bedeviled predictors for centuries. With these two laws, the moon's path was no longer a mystery. It was a precise, calculable curve. Kepler compiled all of this hard-won understanding into his Rudolphine Tables. These star catalogues and planetary tables were the most accurate of their age, a practical tool that allowed any astronomer to compute the positions of celestial bodies with newfound reliability. For eclipse prediction, this was a quantum leap. The tables accounted for the moon's elliptical orbit and its changing speed, enabling forecasters to determine not just the date of an eclipse, but its exact timing, duration, and the precise path of its shadow across the Earth's surface. Kepler's work completed a profound transformation. He bridged the vast gap between Tycho's raw observations and universal physical laws. He demonstrated that the cosmos was not governed by perfect philosophical ideals, but by rigorous, discoverable mathematics. Eclipse prediction was no longer an art of tracking cycles, it was a science of calculating orbits. The final piece of the puzzle, however, was still missing. What was the invisible force that bent these perfect ellipses and orchestrated this cosmic ballet? The final piece of the cosmic puzzle would be found not in a new law, but in a new lens. When the telescope first appeared in the early 17th century, it tore the heavens wide open. Suddenly, the moon was not a perfect, smooth sphere, but a world in its own right, scarred with mountains and pocked with vast craters. Galileo Galilei, turning his own spyglass to the sky, saw sunspots blemishing the face of the sun, proving it was not an immutable, perfect body, but a changing, physical one. These observations shattered the ancient Aristotelian belief in a perfect, unchanging celestial realm. For eclipse prediction, the telescope's power was not in forecasting the timing of an event, but in understanding its very nature. Astronomers could now measure the apparent sizes of the sun and moon with unprecedented precision. They discovered that these sizes were not constant, but varied slightly as the Earth and Moon moved along their elliptical paths. This was critical. The precise diameter of the lunar shadow and whether it would completely cover the sun or leave a brilliant ring of fire depended on these exact measurements. A telescope could not tell you when the next eclipse would occur, but it could tell you exactly what kind of eclipse it would be. This new tool transformed astronomy from a science of positions to a science of physical bodies. It provided the hard data needed to refine the mathematical models of Kepler and his successors, verifying their predictions against a newly visible reality. The telescope was the ultimate validator, a mechanical eye that confirmed humanity was finally reading the cosmos correctly. Isaac Newton saw the universe as a great machine governed by a single, elegant force. His law of universal gravitation revealed that the very same pull that brings an apple falling to the ground also keeps the moon tethered to the Earth and the Earth bound to the sun. This was a monumental unification. Suddenly, the cosmic dance was not just a set of geometrical rules, but a dynamic interplay of physical forces. In his Principia Mathematica, Newton provided the mathematical language to describe this force, demonstrating how every body in the universe attracts every other body with a strength proportional to its mass and inversely proportional to the square of the distance between them. For eclipse prediction, this was a game changer. The moon's orbit was no longer a simple, clean ellipse. Newton's equations showed that the sun's gravity constantly tugs at the moon, subtly distorting its path around the Earth. These tiny gravitational tugs, called perturbations, cause the moon's orbit to wobble and shift over time. A predictor using only Kepler's ellipses would eventually find their forecasts drifting out of sync with reality because they were missing these crucial gravitational nudges from the sun. Newton's framework allowed astronomers to calculate these perturbations to account for the sun's relentless pull on the Earth-Moon system. This meant they could now forecast not only the basic occurrence of an eclipse, but its most minute details with a precision that felt almost supernatural. The old geometrical models, for all their sophistication, were like predicting the path of a leaf in a stream by tracing its past movements. Newtonian mechanics gave you the physics of the current itself. It replaced description with causation, explaining not just how the bodies moved, but why they had to move that way. This new standard of predictive power transformed astronomy into a truly physical science, one where the clockwork of the heavens could be understood and anticipated down to the very second. How far could this new understanding take us? Could we now predict every eclipse anywhere on Earth for all of time? Newton's laws provided the universal rules, but applying them to the messy reality of the solar system was a monumental mathematical challenge. The moon's path is a constant cosmic tug-of-war, pulled not only by the Earth but also by the distant yet massive sun, and even to a tiny degree by the other planets. These extra gravitational tugs, known as perturbations, are what make the moon's orbit subtly shift and wobble over time. Even the most perfect ellipse, as described by Kepler, is slowly deformed by these invisible forces. For an eclipse predictor, this was the final frontier of precision. A forecast made years in advance could be thrown off by mere minutes, or the shadow's path shifted by miles, all because of a gentle pull from Venus or Jupiter. The problem was no longer understanding the primary force, but calculating the combined effect of every other body in the system. This demanded a new kind of mathematics, one capable of modeling a universe of constant, interacting motion. The stage was set for the mathematical virtuosos of the Enlightenment. Figures like Leonhard Euler and Joseph Louis Lagrange took up the task, developing powerful new branches of calculus and celestial mechanics specifically to solve the many-body problem. They created perturbation theories, sophisticated mathematical frameworks that allowed astronomers to quantify these tiny gravitational nudges. Think of it as predicting the path of a sailboat not just by the wind, but by accounting for every current, every wave, and the gravitational pull of the moon on the water itself. Their equations could trace how a planet's influence would slowly change the orientation of the moon's orbit, altering the timing of an eclipse by a few crucial seconds, or determining whether a city would see a total eclipse or just a partial bite taken from the sun. The most tangible output of this mathematical revolution was the creation of supremely accurate ephemerides. These were elaborate tables predicting the future positions of the sun, moon, and planets with a level of detail previously unimaginable. An astronomer could now open a volume of these tables and find the moon's precise location for any given hour, years into the future, with the perturbations already calculated and included. This collaboration between theoretical mathematicians and practical astronomers transformed eclipse forecasting from an art into a highly computational discipline. It underscored a profound truth about our universe, that to predict the dance of the heavens, you first had to master the language of mathematics. This relentless pursuit of precision was about to be tested in the most public way possible, as a total solar eclipse cast its shadow across the face of a modernizing Europe. The immense computational power of celestial mechanics needed a new kind of home. It was no longer enough for a lone astronomer to work from a private observatory. The science now demanded scale, coordination, and permanence. This need gave rise to the National Observatory, an institution dedicated not to personal glory, but to the systematic, relentless collection of data for the public good. Places like the Royal Observatory at Greenwich, founded in 1675, became the great clearinghouses of the heavens. Their mission was to create a perfect, standardized map of the sky, a project that would span generations and continents. The first astronomer royal, John Flamsteed, spent his entire career measuring the positions of over 3,000 stars with painstaking care. His catalogue, published posthumously, was not a theoretical exercise. It provided the essential fixed backdrop against which the moon's wandering path could be measured with unprecedented accuracy. Without this stable grid of reference points, predicting the moon's precise location for an eclipse was like trying to measure the speed of a car without knowing where the road was. His successor, Neville Maskelyne, pushed this institutional approach even further. He standardized the observatory's methods and published the Nautical Almanac, an annual volume of celestial data that gave sailors and astronomers alike the predicted positions of the sun, moon, and planets. This was data as a public utility, a tool that transformed navigation and, crucially, eclipse prediction from an esoteric art into a repeatable, verifiable science. The true power of these institutions, however, lay in their global reach. A solar eclipse sweeps across the Earth, its shadow touching different continents. By coordinating observations from astronomers stationed at different longitudes from the Americas to Asia, the Royal Observatory could collect multiple timings of the same event. When an eclipse began a few seconds later in Cape Town than predicted, and a few seconds earlier in Bombay, that discrepancy was not a failure. it was priceless data. These coordinated efforts revealed the subtle imperfections in the lunar tables, the tiny gravitational perturbations that the mathematicians were still struggling to quantify. Each carefully recorded observation from a distant outpost helped to nudge the models closer to perfection. This was the birth of big data in astronomy, a collaborative, institutional effort that ensured the quest for precision would no longer depend on the life of a single individual, but would become the enduring mission of science itself. The sheer complexity of the moon's motion demanded a new kind of mathematics, one that could tame the endless columns of numbers. The 19th century answered this call not with a new theory, but with a revolution in calculation itself. Astronomers now wielded powerful tools like logarithms and mechanical calculators, devices that could slice through the dense thicket of arithmetic that once took weeks to complete. Friedrich Bessel became a master of this new craft. He developed what we now call Besselian elements, a set of mathematical functions that acted like a master key for any eclipse. Instead of recalculating the entire gravitational dance from scratch for every single event, an astronomer could plug a few key numbers into Bessel's standardized formulas. These elements distilled the sun and moon's positions, their relative speeds, and the tilt of their orbits into a set of clean, manageable numbers. From this data, one could derive everything: the exact time the eclipse would begin for any town on the map, the duration of totality, and even the angle at which the moon's shadow would first touch the Earth. It was a system of breathtaking efficiency. This computational leap transformed eclipse predictions from abstract astronomical events into tangible, local forecasts. For the first time, a ship's captain could consult a newly published Nautical Almanac and know that on a specific date, at a specific hour and minute, darkness would fall upon a particular stretch of ocean. An educator in a small town could point to a detailed map in a popular science magazine, tracing the very path of the moon's shadow across the continent. These publications demystified the heavens, bringing precise celestial mechanics into the hands of the public. The ultimate test of this new precision came when astronomers could not only say an eclipse was coming, but could draw a narrow black line across a map, declaring with confidence, here, and only here within this ribbon of shadow, will the sun be completely extinguished. This was the moment eclipse prediction became a practical, geographical science, a tool for planning expeditions and thrilling the masses. It proved that humanity had finally decoded the cosmic schedule, but knowing the schedule was one thing, understanding the profound new discoveries waiting in that brief, artificial night was another matter entirely. Even the most perfect Newtonian clockwork held a hidden, slow drift. By the 18th century, astronomers had a powerful new tool at their disposal: ancient eclipse records. When they compared their precise modern calculations with the descriptions of eclipses seen by the Babylonians and the Chinese thousands of years earlier, they found a small but stubborn discrepancy. The moon was ever so slightly ahead of schedule. Its orbit was not a fixed ellipse, it was a slowly unwinding spiral. This tiny mismatch, accumulating over centuries, revealed a profound truth: the Earth-Moon system is not static. The moon is gradually moving away from us, and its orbital period is lengthening by a barely perceptible amount each year. This is the moon's secular acceleration, a change so slow it can only be seen across millennia. The cause of this cosmic drift lies in the ocean tides. The gravitational pull of the moon creates a tidal bulge in Earth's oceans. But because Earth rotates faster than the moon orbits, this watery bulge is dragged slightly ahead of the moon. This leading mass of water then exerts its own gravitational pull, gently tugging the moon forward in its orbit, giving it a tiny push that slowly pushes it to a higher, slower path. It is a subtle transfer of energy from Earth's spin to the moon's orbit. Pierre-Simon Laplace, the great French mathematician, was the first to tackle this puzzle with full mathematical rigor. He incorporated the gravitational effects of the planets and this tidal interaction into his monumental work on celestial mechanics. By quantifying this slow acceleration, he could finally make the ancient records agree with his modern predictions. His equations showed that the orbits of celestial bodies are not frozen in time. They are dynamic relationships, constantly evolving. This meant that to predict an eclipse with perfect accuracy for the year 3000, you could not simply reuse the calculations from the year 2000. You had to account for this relentless, gentle push, this slow dance of separation between our world and its companion. The discovery of the secular acceleration was a humbling reminder. It proved that our cosmic neighborhood is a place of constant, subtle change, and that true prediction requires us to listen to the whisper of the tides across astronomical time. A new technology emerged that would freeze the celestial dance in time. Photography transformed the eclipse from a fleeting spectacle into a permanent document. Before the camera, an astronomer had to sketch the sun's corona in the frantic 2 minutes of totality, their hand trying to capture a complex vision of pearly light against a racing clock. Human memory and manual dexterity introduced unavoidable errors, but with a photographic plate, every delicate streamer and every faint prominence of the corona could be captured with impartial precision. The very first successful photograph of a total solar eclipse was taken in 1851, and it opened a new window onto the sun. Astronomers like Warren de la Rue designed special photoheliographs, telescopes adapted to hold glass plates coated with light-sensitive chemicals. During an eclipse, these instruments would track the sun, their shutters clicking open to let the ghostly corona etch its own portrait directly onto the glass. This was more than just a pretty picture, it was hard data. Scientists could now measure the exact extent of the corona, study its structure, and compare its appearance from one eclipse to the next, year after year. For lunar eclipses, photography provided an irrefutable clock. A timed sequence of images could pinpoint the exact moment the Earth's shadow first touched the moon's limb, and the instant it finally retreated, with an accuracy far beyond the human eye. This flood of new, consistent data was a gift to the mathematicians. Their predictive models, built on Newton's laws and Bessel's elements, could now be tested and refined against a perfect, unblinking record. The camera did not just prove the predictions were right, it revealed the subtle details they needed to explain next, pushing our understanding of the sun's mysterious atmosphere into a new era of empirical science. Out on the open ocean, far from any landmark, a total solar eclipse was more than a spectacle. It was a celestial clock. For centuries, the greatest challenge for any mariner was determining their east-west position, their longitude. A navigator could easily find his latitude by measuring the height of the sun at noon, but longitude required knowing the precise time back at his home port. An error of just a few minutes could mean missing an island by dozens of miles, a potentially fatal mistake. An eclipse provided the solution. Astronomers on land could predict the exact moment an eclipse would begin or end for a specific location, like Greenwich, England. A ship's captain, armed with this forecast and a reliable clock, could observe the same eclipse from the deck of his vessel. By noting the local time the event occurred and comparing it to the predicted time for Greenwich, he could calculate his longitude. The difference in time directly translated to a difference in position. Every minute the local event was late compared to Greenwich meant the ship was that many miles to the west. This method transformed a terrifying celestial omen into a crucial navigational fix, shrinking the uncertainties of the vast oceans. The famous explorer Captain James Cook carried precise eclipse predictions on his voyages into the uncharted Pacific. During his first voyage, he observed a solar eclipse from a location now known as Cook's Bay in Tahiti. His meticulous recording of the event allowed the Admiralty back in London to verify the accuracy of their charts and his own navigational skills. For these explorers, the ability to forecast an eclipse was a direct form of power. It reduced the risk of long voyages, enabling the expansion of global trade routes and the mapping of new continents. This was the ultimate practical test of astronomical knowledge, where abstract mathematics and celestial mechanics directly guided ships through perilous waters and brought the distant corners of the world into contact. The same cosmic cycles that once dictated the fate of emperors were now charting the course of empires. While grand observatories charted the stars, another vital force was quietly at work in backyards and on remote hilltops. Amateur astronomers armed with passion and increasingly affordable telescopes have become the global sentinels of eclipse science. Their strength lies not in billion-dollar instruments, but in their sheer numbers and geographic reach. A total solar eclipse carves a narrow path across the planet, often sweeping over remote oceans or sparsely populated lands where no professional team can be stationed. An amateur astronomer, however, might be waiting there, camera ready, to capture the event. These dedicated enthusiasts provide crucial ground truth, filling in the gaps that satellite imagery and theoretical models cannot. They are the human network that blankets the globe, turning a single celestial line on a map into a rich tapestry of localized observations. Their contributions transform an abstract astronomical prediction into a documented physical fact. Organizations like the British Astronomical Association have long understood this power. For over a century, they have masterfully coordinated these dispersed observers, turning individual curiosity into a collective scientific instrument. They provide standardized observation forms, detailed protocols for timing and photography, and a central repository for the gathered data. During an eclipse, a single professional team can only be in one place, but a coordinated army of amateurs can be stationed every few miles along the entire path of totality. This dense network is essential for studying elusive phenomena like shadow bands. These mysterious, rippling patterns of light and dark that race across the ground just before and after totality are poorly understood and notoriously difficult to capture. With dozens of amateurs filming the same event from slightly different angles, scientists gain a multi-dimensional view that helps unravel their cause. Similarly, the precise timing of Bailey's beads, those brilliant points of sunlight flashing through the lunar valleys, helps refine our knowledge of the moon's exact topography. Each carefully recorded observation is a piece of a larger puzzle. The value of this work extends beyond a single event. Amateur records create a continuous thread through history, a long-term dataset that professional astronomy, with its focus on cutting-edge questions, often cannot maintain. An amateur might dedicate a lifetime to observing eclipses, building a personal archive that spans decades. This longitudinal perspective is priceless for spotting slow, subtle changes. When a professional researcher needs to check an anomalous reading from a century ago, they often turn to the meticulously kept journals of a past amateur. This partnership is a beautiful symbiosis. Professionals provide the theoretical framework and the grand questions, while amateurs supply the widespread, persistent eyes on the sky. They are the citizen scientists who verify the supercomputer's prediction with a simple stopwatch and a keen eye, grounding our most advanced cosmic models in the enduring tradition of human wonder. What new mysteries might this global collaboration unlock as the moon's shadow continues its endless journey around our world? Einstein's theory of general relativity wove gravity into the very fabric of space and time. It proposed that massive objects like the sun warp the space around them, causing even light to bend as it passes nearby. This meant that during a solar eclipse, when the moon blocks the sun's brilliant face, the stars appearing just beside the darkened sun would not be in their true positions. Their light, skimming the sun's gravitational field, would be deflected, making them look slightly shifted. In 1919, this radical idea was put to the test. Two expeditions, one to the island of Principe and another to Sobral in Brazil, aimed to photograph the stars visible during totality. Their careful plates showed a tiny but definitive shift in the starlight, exactly as Einstein had predicted. The universe, it turned out, operated on a geometric stage where gravity was not just a force, but the curvature of space-time itself. For eclipse prediction, this introduced a subtle new consideration. The apparent position of the sun and moon, the very actors in the eclipse drama, are also minutely affected by their own gravitational fields. The light we use to track them follows curved paths. In practice, for a single eclipse, the effect is incredibly small, altering timing calculations by mere fractions of a second. But for the precise cosmic accounting required over vast timescales, this relativistic correction becomes essential. It exemplifies a profound truth in science that even our most reliable tools must evolve. Newton's clockwork universe was magnificent, but Einstein revealed it was built on a flexible, dynamic fabric. The confirmation during that famous eclipse did more than prove a theory. It demonstrated that to predict the heavens with absolute fidelity, we must now account for the invisible architecture of space itself. Today, the ancient art of eclipse prediction lies within the silent hum of supercomputers. These modern oracles run on lines of code, performing numerical integration, a mathematical process that essentially simulates the solar system frame by frame into the future. Instead of relying on a single cycle or a fixed equation, these models calculate the gravitational pull between every significant body, from the giant Jupiter to the tiny moon, for every second of every day for centuries to come. They account for the moon's slow recession, the Earth's wobbling spin, and the subtle tugs of relativity, creating a dynamic, living map of celestial motion. At the forefront is software like NASA JPL Horizon system, which can generate a precise trajectory for the moon's shadow for any location on Earth, decades from now. The path of totality for an eclipse in the year 2050 is already known. Its narrow black line drawn across digital globes with an accuracy of meters. This incredible precision is fed by a constant stream of new data from lunar laser ranging experiments that bounce light off reflectors left by Apollo astronauts, and from spacecraft that map the moon's gravity field in exquisite detail. We are no longer just predicting the sky, we are virtually recreating it, and this power is no longer locked away in observatories. That same computational force now fits in your pocket. Through websites and smartphone apps, anyone can pull up an interactive map for the next eclipse, seeing exactly when it will start in their backyard, how long it will last, and what percentage of the sun will be obscured. The knowledge that was once the sacred domain of kings and priests, painstakingly calculated over a lifetime, is now a free public utility. This is the final evolution of a quest millennia in the making, a journey from clay tablets to quantum chips, all driven by our timeless desire to know when the light will return. This intellectual inheritance now lives far beyond the observatory walls. The same cosmic clockwork that fascinated ancient Babylonians now inspires modern artists who paint the sun's corona in swirling oils, and filmmakers who use computer graphics to recreate the moon's shadow sweeping across a planet. Literature is filled with eclipses as powerful narrative turning points. moments of divine intervention or personal revelation that echo the awe our ancestors felt. This cultural resonance underscores a simple truth. Our drive to predict these events was never just about the numbers. It was about the human story unfolding beneath them. Today, that story continues in classrooms around the world. A solar eclipse is a perfect, ready-made laboratory in the sky. Teachers use its predictable arrival to demonstrate geometry, showing students how to use similar triangles to calculate the sun's immense distance. They explore the history of science, tracing the long chain of reasoning from Thales of Miletus to Einstein, and they hand out sheets of white paper, teaching young observers to project a tiny crescent sun image, recreating the same wonder that Galileo must have felt. This hands-on engagement turns abstract principles into tangible experience, proving that the cosmos is not a distant concept, but a dynamic presence in our lives. Even as science explains the mechanics, the old myths persist, not as competing truths, but as cultural treasures. In many parts of the world, people still bang pots and pans during an eclipse to scare away the mythical beast swallowing the sun. These rituals are a testament to the enduring power of the event, a connection to our collective past that science enriches rather than erases. The entire history of eclipse prediction is, in itself, a masterclass in the scientific method. It shows us how patient observation leads to pattern recognition, how a hypothesis is tested against new data, and how models are refined over centuries through collaborative, often cross-cultural effort. The Mayan tables, the Greek geometries, and the Islamic star catalogues were not isolated triumphs. They were threads in a single, global tapestry of inquiry. This legacy is a profound reminder of our shared humanity. It connects the Chinese court astronomer trembling before his emperor to the modern family watching a live stream, all united by the same celestial spectacle. Our quest to understand the eclipse reveals just as much about our own enduring curiosity, our need to find order in the heavens, and our timeless place under the sun and moon. From the clay tablets of Babylon to the computer models of today, this entire journey stands as a powerful testament to human curiosity. That uncanny precision achieved by early astronomers was not a gift but a hard-won victory. It was forged through generations of patient observation, through mathematical leaps of genius, and a cultural dedication so profound it spanned centuries. They laid the entire foundation for modern science with nothing more than their eyes, their minds, and an unwavering belief that the universe operated on principles we could understand. Their story is a humbling reminder that technology is a powerful tool, but it is human ingenuity that truly unlocks the secrets of the cosmos. Our own explorations, from telescopes to space probes, are built upon the scaffold they erected stone by stone. As we continue to push the boundaries of knowledge, looking toward Mars and beyond, we honor these pioneers best by nurturing that same sense of wonder and relentless inquiry in the generations who will follow. What historical mysteries from the ancient world capture your imagination? Share your thoughts in the comments below and subscribe for more journeys into the profound secrets of our past.